Hello everyone. Now we can discuss about Manacher's algorithm. This algorithm helps us to find the longest palindromic substring in the given string. There are some other algorithms that finds the longest palindromic substring in the given string. But the importance of Manacher's algorithm over them is it can be done in linear time, where native approaches takes order of n square time complexity. Let's see an example for Manacher's algorithm. Consider a string A, B, A, B, A, B, A. As we see here, there are many palindromes like A, B, A, B, A, B, A, and A, B, A, B, A, B, A whole string. To make our algorithm works for both odd and even length strings, we want to make some changes in the original string. Let that modified string would be now this @ and this dollar is to identify the leftmost and rightmost boundaries of the string. Now let's consider an array P that helps to find the expansion length at each character. First, consider all the values as 0. These are the indexes of the array. Now let's initialize two variables C and R that here C is the center of the longest palindrome and R is the rightmost boundary of the palindrome. Initialize C and R to the first character, which is our hash at index 1. As our I is at index 1, now check the mirror position. Now check the mirror position of index 1 centered at C. For that mirror equal to 2 into C minus I. Here our I value is 1 and C value is also 1. So 2 into 1 minus 1, which is equal to 1. So here the expansion length is 0. So there is no change. Now move for the next iteration, where our I is here. I is at index 2. Now check for the mirror position of this index, which is 4 minus. Now we are at index 2. Let's see the mirror position of this. Here C value is 1 and 2 into 1 minus our I value is at 2, which is 0. At 0 the expansion length is 0, so there is no change. Now try to expand at index 2. Here check the characters at left and right side. Here both the characters are same, so increase the expansion length by 1 and keep on checking that. But here @ and B is not same, so move out of that checking and check for the condition. If the rightmost boundary of the palindrome centered at I is less than the current longest rightmost boundary of the palindrome, which is R, then we want to update the values of this center and R. Here R is positioned at index 1, but our expansion is up to index 3. So we want to update the C and R values. Our C is now at index 2 and R is at index 3. Now move on to the next iteration where our I is positioned at index 3. Again check for the mirror position of index 3 where C is the center, C which 2 is the center. Now 2 into 2 minus our I value is 3 which is equal to 1. Now the value at expansion length at index 1 is 0. So take that value only. Then try to expand at index 3 but the left and right characters are not same. So move to the next iteration. Now our I value is at index 4. Again try to find the mirror position of index 4 centered at index 2 which is 2 into 2 minus 4 that is equal to 0. In the expansion length at 0 is 0, so the expansion length at this index is first starting at 0. Now try to expand the palindrome. So the left and right characters are same, so increase it by 1. Again keep on checking. Here A and A also same. Again increase 2. Then again it will increase to 3. And after checking that at the right and B are not same, so it stops at here. Now the expansion length at this index is 3. But this is the expansion is up to index 7. But the rightmost boundary of current longest palindrome is at index 3. So we want to update the center and rightmost boundary positions where our C is at index 4. This is our C and R is at index 7. Now move to the next iteration where our I is positioned at index 5. Now check for the mirror position of index 5. Here our center is 4, so 2 into 4 minus our I value is at 5 which is 8 minus 5, it is 3. The value at 3 is 0, so it will be 0 only. Next try to expand at index 5. Keep on extending, both the characters are not same, so move to the next step where our index is positioned to 6. Now check for the mirror position. 2 into 4 minus 6 which is 2. Here the value at expansion length at index 2 is 1, so we want to make this value to be 1. And after that as we want to check for expansion at that index, we already know that this position is expanded right side and left side with a value 1. So we are not required to check for this and this character, and we want to check after this side, after this character, and after this side this character. So check for this B and B, both the characters are same, so increase the value by 1, it is 2. And then again we want to check again hash and hash, then also increase 3. Again we want to check it's A and A, then 4. Again it's hash and hash, it's 5. And at this point it is at the rate and B, which is not same. So we want to check for the condition if the expansion is beyond the previous rightmost boundary. As we can see that our R is positioned at index 7, but our expansion is up to index 14. So we want to update this center and R values. Our center is at index 6, our R value is at index 11. Now so next move to the next iteration where our I value is at index 7. Same like this, we want to check for mirror position, which is 2 into our center value. Center is at index 6, so 2 into 6 minus our index value is 7. 6 2 is 12 minus 7, which is 5. At index 5 the expansion length is 0, so we want to keep it 0 only. Then try to expand at index 7. At index 7 there is B. Check for left and right characters. Here it's same, so increase by 1. Then again same 2, then again same 3, then again same 4, again same 5, again same 6, and then also it is same 7. At last it is different, so the value is increased up to 7. Now we want to check for the condition that our expansion is beyond the previous rightmost boundary or not. Yes, our expansion is beyond the previous rightmost boundary. Now our expansion is up to 15 and the previous rightmost boundary is at 11. So we want to update this. Our R is at index 15 and the C is at index this point. Now next we want to move to the next iteration. On keeping on this, there is no more palindrome greater than this. On keep on doing this, we got here 5 0 and then here 0 3 and here 1. As we completed all the iterations, now we want to check for the maximum among these. As we start at index 0 and check up to 16, then we will find this position as the longest expansion position. Now we want to extract the substring from this original string. For that we want to, for starting index of the original string, start index, which is equal to here the centered index, which is 7, centered index it is 8 and the maximum length which is 7 and this by 2, which is equal to 1 by 2, that is 0. So starting index in the original string is 0 and the ending index is the maximum length, which is 7. Our original string is ABA, so let's index it 0 1 2 3 4 5 6. As we see that the starting index is 0 and last index is 7, last maximum length is 7. The whole string is the longest palindromic substring in the given string. Now let's see the analysis of time complexity and space complexity. The first step we did in this algorithm is we converted the original string to some modified string. For this we need of n time, and then we at every character we are expanding it, so it will be maximum of again O of n. At the end we are again searching for the maximum expansion length. For this also we need to traverse through all the characters in the string. It is also of O of n. Here the time complexity is always O of n and it is not more than that. So the final time complexity of Manacher's algorithm is O of n, which is linear time. And the space complexity is we are taking a single array string and this array which is of at most maximum 2n length, so it is also linear. So the space complexity of Manacher's algorithm is also linear, which is O of n. The major applications of Manacher's algorithm is that DNA sequence analysis, text processing and pattern recognition and many other like this. The conclusion of this Manacher's algorithm is that its linear time complexity and practical applications underscore its significance as a foundational tool in the computer science. So this is all about the Manacher's algorithm. Thank you for watching.